Hello everyone, Victor is here, your organic chemistry tutor, and in this video I want to talk about the alpha-halogenation of aldehydes and ketones in both basic and acidic conditions. This is a fairly common reaction that you can expect on the test, so it is definitely a must-know reaction. On top of that, I do want to talk about the haloform reaction, which is basically a halogenation of carbonyls on steroids. And the big difference here is going to be that it is done whenever you are dealing with the ketone containing the methyl group, and we have basic conditions in excess of both base and the halogen. But we'll get to that in a few moments here. For now, let's take a closer look at our reaction, starting with the acid-promoted halogenation reaction. In acidic conditions, carbonyls undergo enolization, making a corresponding enol. I have another tutorial on the enolization equilibrium, so if you need a refresher on that, make sure you check out that video first before continuing, because we are going to deal a lot with the keto-enol tautomerism throughout this video. But let's get back to our keto-enol tautomerism for right now. Enols are typically going to be minor components of this equilibrium, but what is more important to us is the fact that the enols are nucleophilic. And of course, when it comes to the halogenation, halogens are electrophilic. For the illustrative purposes in this video, I'm going to be using bromine, but it can just as easily be iodine or chlorine. But what is equally important to us is that halogens like bromine, chlorine, iodine, those guys are electrophilic. And so what happens when a nucleophile and electrophile are together? Well, they are going to react with each other. So if we look at the mechanism of this reaction, I'm going to start by taking a sample molecule. In this case, I'm going to start by looking at my acetophenone, the molecule that I have over here on the left, and I'm going to react that with acetic acid and bromine for my halogen. Acetic acid is a very common solvent and the catalyst for this reaction, while the bromine, of course, here is going to be a reagent. We're going to start this reaction by protonating the carbonyl of our ketone over here with our acid. That's going to give us a protonated species. The next step is going to be to deprotonate the alpha position, the position next to our carbonyl. This carbon over here, we are going to normally refer to that as the alpha position. So once we deprotonate that thing with the conjugate base that we have floating around, we are going to end up with the corresponding enol. And as we already know, enols are nucleophiles. So next, I'm going to bring my halogen, my bromine, over here. And as I have already mentioned, bromine is an electrophile. So the way it's going to work, we're going to take these electrons that we have on the oxygen, and we are going to do a cascade of the electron density where we are going to essentially end up making a new bond between this carbon over here and a bromine atom. We could have, of course, used the minor resonance structure that I have over here for my nucleophilic enol, but it's a good idea to draw resonance structures only when we need them, and if we are going to be drawing any kind of resonance structures, it's always a good idea to use the major contributors, and in this case the major contributor is going to be the uncharged enol form. So once I do the reaction with my uncharged enol form, which is this guy, with my halogen over here, I'm going to form the following protonated intermediate. And as I mentioned a moment ago, this one over here is going to be my new bond, so I'm going to designate it as NB for the new bond. Since this is a protonated species and we generally prefer to write neutral species as our final products, we are going to get rid of this proton over here, and in order to do so, I am either going to be using my Br- that is floating around from the previous step, or I could potentially use the acetate anion, which is coming from our solvent/catalyst here. This is a conjugate base for the acid that we are using. So if I am going to show it with my Br-, I will show these electrons coming in and grabbing our proton, giving me my final product looking like this, where I have replaced one of the hydrogens in the alpha position to my carbonyl with a bromine atom. And because we have the halogen in the alpha position to our carbonyl, some instructors will refer to that as the alpha-halogenated carbonyl, and some textbook will refer to that as well. Now, there is something very important that I want to mention here that has to do with the kinetics of this reaction in acidic conditions. The very first step in this reaction, as I've mentioned a moment ago, is a protonation of our carbonyl. It is a proton transfer. Normally, we think about proton transfers as an extremely fast reaction. However, in this case, this is actually going to be a rate-determining step, so it is going to be one of the slowest steps in this entire mechanism. And that fact has very important consequences for this reaction. As each bromine atom going to pull the electron density towards itself, the more bromines we put onto the molecule, the stronger that pull of the electron density is going to be. And while theoretically we can continue this reaction until all the hydrogens in the alpha position going to get substituted with bromine, each reaction is going to become slower and slower and slower, as each bromine going to be essentially making our oxygen less and less basic, and the reaction of protonation, the very first step, is going to become less and less favorable. And as protonation becomes less favorable, we are essentially going to stop at the formation of the first product, and we are not going to proceed with the other ones. So the other two possible products are typically not going to be observed when we are dealing with this reaction in acidic conditions. So remember, in acids, we're only going to react once. Now, once we get to basic conditions, that is where things become a little bit more interesting. Typically, whenever we are going to be doing this reaction in basic conditions, the most common base of choice is going to be something like sodium or potassium hydroxide. And like in the previous case, the very first part of the mechanism is going to be the enolization of our starting material. I'm using the same starting material as before, and the very first step here is going to immediately enolize our molecule like so, giving us an enolate intermediate. And I want to remind you here that enolates are more nucleophilic than enols due to the fact that now we have this negative charge over here. So overall hybrid that we are going to have spreading the negative charge over these atoms is going to have a much higher electron density, and because of that it is going to be significantly more reactive with electrophiles. So when I bring my electrophile around, which is going to be bromine in this case, just like in the previous case, what we're going to see is a similarly looking reaction, similar style electrophilic attack from our bromine onto our nucleophile, giving us our product right away. And like in the previous case, my new bond is right over here between the alpha position and my bromine atom. But that's where the fun only begins. The thing is, the bromine atom that I have sitting over here, as we know, that is an electron withdrawing group. And what that means is that it's going to pull electron density towards itself. Unlike in the previous case where we needed to have electrons on our molecule to protonate that, in this case we are deprotonating the molecule. And since we are still working in basic conditions, I'm going to show my OH- over here. Now, if I attempt to deprotonate my molecule again, well, in this case, this process is going to be even easier than the original one, because these two protons that I have over here, because of this bromine, because we have the electron withdrawing group, these protons now are more acidic. And we are immediately going to reform our enolate again. Now, that enolate already contains one bromine, and for as long as we have more of our electrophile floating around, and we have another molecule of bromine, well, our nucleophilic enolate can now react with our electrophilic bromine again, giving us product with two bromines in the alpha position. But now guess what? Because we have two of those bromines, and both of those bromines are pulling electron density towards itself. We have this bromine, we have that bromine, both of those are electron withdrawing groups, well, that means that this proton that I have over here now is even more acidic than what we had in the previous case. So that essentially means that another equivalent of base that I have floating around can easily come in, pull that proton off even easier, reforming an enolate again, and reacting with another equivalent of our bromine like so, doing another electrophilic attack, and giving us the final product where we now see the exhaustive halogenation in the alpha position. And this one over here, this is how I abbreviated my electrophilic attack. This is not an E1 attack, just so we're clear on that. So the important take-home message here is that when you are doing this reaction in basic conditions, you gotta replace all alpha hydrogens with the halogen. And you might protest here saying that, well, just use one equivalent, what's the big deal? Well, the problem here is that every step in this reaction becomes faster and more efficient as we're adding halogens to our molecule. So while the first step in this reaction, giving you the initial product over here, is efficient, the next step, giving you a product with two bromines, is even more efficient. And the next step, giving you a product with three bromines, is even more efficient. So unfortunately, it is impossible to stop it by just controlling the quantities of your reagents. It's like rolling down the hill. You are going to be accelerating whether you want it or not, and there are no brakes in this reaction. It will be exhaustive. So this reaction is always done in excess of reagents, otherwise you are just going to get a soup of all possible products, and you are not going to get what you are looking for, because it's going to be literally everything that is possible here. You are going to see it. So the excess of our reagent will guarantee that at least we are going to get an exhaustive halogenation rather than just stopping somewhere in a weird middle. So if you only want to place one halogen, you are going to do this reaction in acidic media, and if you want to do exhaustive halogenation, you are going to do it in basic media. Now, I did mention at the beginning of this video that we are going to talk about the haloform reaction as well. So let's look at the product of our last reaction where we did the halogenation in the basic conditions. This guy over here that I have right over there. I'm going to redraw this molecule, and I'm going to look at it very carefully, because now I've mentioned that bromine is a very good electron withdrawing group, which does mean that this entire moiety in our molecule over here essentially becomes an exceptional electron withdrawing group as well. But it's not only an electron withdrawing group, it is also a leaving group that can potentially be replaced by a nucleophile if we have a suitable nucleophile in the reaction. And we know that reaction of halogenation in basic conditions is done in the base, so we absolutely do have a suitable nucleophile around in the form of our base, our OH-. So what can happen here is now, since there are no protons in the alpha position, we are going to go after the carbon of the carbonyl instead. And we are going to perform a nucleophilic attack on the carbonyl, giving us a tetrahedral intermediate that will love from all of those acyl substitution reactions. And I do have a video on the acyl substitution reactions, so if you need a refresher, or maybe you haven't heard about those reactions to begin with, you can learn more in this video, and of course all the links are going to be in the description below. But back to my reaction here. Now, since this is a leaving group, it means that we can easily kick it out, like so, where the electrons from the oxygen going to cascade down and displace that leaving group, giving us a couple of rather interesting products. We have a carboxylic acid, this part over here, and we have CBr3-. That CBr3- species is actually fairly basic, and we are going to use that to snatch the proton off our carboxylic acid immediately, which going to give us the corresponding carboxylate, looking like so, and another species, HC Br3, which is commonly called bromoform, which is a type of a haloform, and hence the name for this reaction, the haloform reaction. Now, the important bit about this last step is the equilibrium constant for this step. The pKa value for the bromoform is estimated to be somewhere around 25, give or take. Now, the pKa for the carboxylic acid, the benzoic acid that I have over here, is about 4.2, or if it is just some sort of a generic carboxylic acid, we can round it to somewhere between 4 and 5, maybe like 4.5, 4.6, doesn't really matter for our purposes. What does matter here is that due to the huge differences in the pKa values of our conjugate acid and the actual acid, the equilibrium constant in this reaction is going to be estimated to something like 10 to the 21st power, which is an astronomical number, which means that there is absolutely no way this last step going to go back. This last step is even silly to call an equilibrium to begin with, but if you really like to call it an equilibrium, you may, I guess. But what that does mean for us is that if we're drawing this reaction, we got to show the final product being the carboxylate and not the acid itself. If we want to obtain the acid, we would have to protonate that acid, which means that most commonly you are going to see aqueous workup at the end, which is going to give you your carboxylic acid as the final product. So the haloform reaction can potentially be a very neat way how you can make carboxylic acids if you need to make a carboxylic acid in your synthesis or in your homework. So when we are going to be doing our halogenation in acidic conditions, we are going to bring in the halogen, we are going to bring in the typically acetic acid as the catalyst and the solvent, although you can see conditions where your instructor just says, acid as the solvent or acid as a catalyst or something like that. That part is not relevant. And we are going to replace only one proton in the alpha position with our halogen. If you are going to do this reaction in basic conditions, we are going to do this reaction again with our bromine. And notice that now I am using excess for my halogen, and likewise for my base, sodium hydroxide in this case, I am also going to be using excess of that because I cannot stop this reaction. And in this case, we are going to end up replacing all of our hydrogens in the alpha position with the corresponding halogen. And remember that if you have a situation like what I currently have over here on the screen, where I have a group like CBr3, well, in that case, I'm going to proceed to the haloform reaction, in which our tribrominated product going to react with our base again, followed by the acidic workup, giving you the carboxylic acid plus the corresponding haloform. It's going to be bromoform in the case of bromination, chloroform in the case of chlorination, and of course iodoform in the case of the iodination. So, for example, let's say I'm going to start with this molecule, 3-pentanone, and I'm going to perform this reaction, this halogenation in acidic conditions. I have two alpha positions where I'm going to potentially replacing a hydrogen with bromine. In this case, there is no difference between our analyzable positions, so it doesn't matter which one we're going to choose. So in this case, I can draw my product like something like that. Now, what if I do the same reaction but now in basic conditions? Since in basic conditions we are going to replace all hydrogens in our alpha positions, my product here is going to look like this. As an extra challenge, I challenge you to actually draw the mechanism for every single step in this entire reaction to show how each of those bromines is replacing the hydrogen in the alpha position. It's going to be a little bit of a long mechanism, but that is an excellent piece of practice for you when you're preparing for the next quiz or the exam. One thing that I want to point out here, that because we only have two bromines in each of those alpha positions, none of that makes a living group, which means that we are not proceeding towards the haloform reaction. We are stopping here. It is an exhaustive halogenation, but we are not chopping off any carbons from this molecule. Now, here is another example, and like in the previous case, I am going to start with the acidic conditions. Here I again have two different alpha positions. I have alpha position on the right side and I have an alpha position on the left side. Since acidic conditions, whenever we're doing the analyzation in acidic conditions, is always going to favor the formation of the most stable enol, which is going to be typically the more substituted enol, we are, in this particular case, going to target this alpha position because that will give us the most stable enol. And again, if you need a refresher on the keto-enol tautomerism, watch my other tutorial on this topic. So because now our alpha positions are not the same, our single substitution product is going to be the product with the bromine on the more substituted atom. So as a rule of thumb, remember that in acidic conditions, you should always put your halogen on the more substituted atom in the alpha position when possible. Of course, if that alpha position doesn't have any protons, there is nothing you can do about that. But if you have a proton on a tertiary alpha position, then put your bromine there rather than on the secondary position. Now, if I start with the same starting material here and do this halogenation in the basic conditions, well, I have the alpha position on the right, I have alpha position on the left. I am not going to choose anything because in the basic conditions we're going to do the exhaustive halogenation, which means that my product is going to look like this when we are replacing all available hydrogens in the alpha positions on both sides of our molecule. And again, since I don't have CBr3 moiety in this molecule, we do not have any leaving group, so we are not going to proceed towards any kind of haloform reactions here. And finally, I have one more example for you. We are going to start with this molecule, and first I am going to do the reaction in acidic conditions. Now here, I only have one alpha position that does contain hydrogens. While technically I do have the alpha position over here as well, that alpha position does not have any hydrogens, which means that we cannot substitute anything there with our halogens, so that position is untouchable for us. And since in acidic conditions we are going to only replace one hydrogen, our final product here is going to look like this. Now, if I were to do this reaction in basic conditions, then I'm going to have something rather interesting happening here. First of all, I'm going to replace each hydrogen in my alpha position with a bromine, but now I do have the leaving group because CBr3 over here is the leaving group, which does mean that this reaction is going to proceed via the haloform mechanism. So we are going to have one more step reacting with sodium hydroxide or whatever other hydroxide base you might have floating around, giving us the corresponding carboxylate plus bromoform in this case. And then once we do our acidic workup, we are going to get our carboxylic acid as the final product. So as you can see, the alpha halogenation of carbonyls is a fairly straightforward reaction. The most important thing for you to remember is that in acidic conditions, you are going to do the substitution once, in basic conditions you are going to do the exhaustive substitution, and if you have the leaving group, you are going to proceed with the haloform reaction. And that's all. As always, thank you for watching, and if you want to learn more organic chemistry, check out this video that YouTube thinks that you are going to enjoy. For more practice questions, go to organicchemistrytutor.com or check the links in the description below, and I'll see you next time.